Hi geometry students, these notes are on the surface area of prisms. So to start we're going to define a term called a polyhedra. It's the plural of polyhedron, and these are solids with polygon faces. So the faces are all of these two-dimensional shapes that make up the three-dimensional solid. And then we say the lines where the faces intersect, so that's all of these lines. These are all called edges. Okay, and so these are polyhedra, or one of them is a polyhedron. And then we're going to look at a specific type. This is one type of polyhedron is the prism. This is a word you might have heard before. So here are three examples. This is a triangular prism, and I'm just going to kind of shade in the two triangles that we see. So we can see like these are two triangles. They form what's called a triangular prism. In the rectangular prism, we can see we have two rectangles there and there, and then they form a rectangular prism, and then this would be a pentagonal prism. Okay, so if we're trying to define a prism, we would say every prism has two bases. So here are my two bases in the triangular prism, here are my two bases in the rectangular prism, in the pentagonal prism, the shaded parts. And the bases of a prism are the parallel and congruent faces. Now, the one thing I want to point out is that in a rectangular prism, there's more that you could consider any of the two opposite faces to be the bases because there are more than one pair of bases of faces that are both parallel and congruent. So it's a little bit of a special situation in a rectangular prism, but in any other one, it's the other shape that forms the base. So then it says the faces of the prism that are not bases are called lateral faces. And so besides the two bases, the lateral faces are always going to be parallelograms. And a lot of the ones we're going to look at is they're always going to be rectangles, and that's because they're a special kind of prism, which would be called a right prism. So a right prism, these are two examples, is where the lateral edges, all these, the edges that make up the lateral faces are the edges that connect the two bases, are perpendicular to the bases. And the other thing that's nice about right prisms is that then all of the lateral faces are rectangles. Now, one quick note I want to make is that when we say a right triangular prism, that triangular base is not necessarily a right triangle, okay? It means that these angles formed with the edges are all right angles, but it could be that none of the three angles in the triangle are right angles. So we say the base not necessarily. It could be a right triangle. Okay. So the key thing that we're going to be calculating in today's notes is surface area of a prism. So we have two different concepts of surface area here. We have the lateral surface area and the total surface area. The lateral surface area is the sum of the areas of only the lateral faces. And then the total surface area would be that lateral area plus the area of the bases. And now we're going to look at some examples on the back. So the first example we're going to look at is, given the right triangular prism shown, find its lateral area and its total area. So if we start with lateral area, that's the area of the three lateral faces, which are the parallelograms. So we have one along the bottom, the one in the foreground, and then the one kind of set back behind. So the first one I'll count is the one that's kind of up here. So it's and I'm going to draw like a little picture of what each face looks like to help me visualize. So this is a rectangle that is 15 by 20. And I know that is going to have an area of 15 times 20, which is 300. And then I'm going to add to that the next face, which I'll do the bottom face next. So for the bottom face, I have to see, well, this length is still 20, right? And it's 20 by now 14. And 20 times 14 is going to be 280. Plus, the last one is the one behind. So this still has a side length of 20, and then it has a width of 13. And that's going to give us a total, an area then of 260. And so the idea is, if I want the total lateral area, I'm going to add up 300 plus 280 plus 260. That's going to give me 840. And that would be my lateral area. Now, you don't have to draw the rectangles each time, but it might be something to help you just kind of organize your information if you're worried about forgetting a face or double counting something. So now that we have the lateral area, we can think about the total area. So for the total area, we're going to take our lateral area and then add to it the area of the two bases. Now note, the two bases are the same. So I'm just going to kind of sketch it once, and then we can think about that times 2. So in this triangle, we know it has a base of 14, and I don't really need the 13 or the 15, I just need the height of 12. So then, if I'm actually going to write out what I'm calculating, I know that the lateral area is 840. I'm adding to that the area of this triangle, which is 1/2 the base of 14 times the height of 12, and then times 2 because I know there are two bases. Okay, now first of all, the 1/2 and the 2 end up just canceling each other out. So this becomes 840 plus 168, which is 14 times 12. So then I get a total area of 1008. Okay, let's look at another example. In example 2, we have a rectangular prism. And here, again, there's more than one pair of faces. There's 3 different pairs of faces opposite each other. The top and the bottom, the right side and the left side, and the front and the back. So it doesn't matter really what I'm calling the bases in this case, because I could make an argument that any of them are the bases. So instead, I'm not going to find the lateral area. I'm just going to find the total surface area. So I'm going to label the lengths on the diagram just to kind of help me with my visualization. And the one thing I notice right away is that there's 2 of each of the bases, two of each of the faces, right? So if I just kind of can identify the dimensions of each of the 3, then I just multiply them by 2. So the one in front is the height times the width. So 10 times 5, and clearly this is not drawn to scale, but that's going to give me 50. And then I'd multiply that by 2 to get 100, right? So that's the first set of opposite and congruent faces. And now the next one is, I'll do the height times the length. So that's 10 times 15. It's going to give me 150. Then I multiply it by 2 and get 300. And then lastly, I'll do the width times the length. So that's 5 times 15. That gives me 75. I multiply that by 2, and I get 150. So then my total area should be the sum of 100 plus 300 plus 150. and that gives me 550 as my total surface area for the rectangular prism. Now, no, none of these problems have units, so I'm just kind of writing up the number, but they are all square units for each of these examples. So maybe I'll just put that. So square units, and square units. Okay, so now moving on to the third example, we have another triangular prism, but it involves a little bit more problem solving because I'm not actually given the height. So first of all, let's find our lateral area, which is the area of the parallelograms. So because both of these sides are 17, I have it twice, so it's going to be, and again, not drawn to scale, 17 by 11, which is 187, and I could multiply this by 2, and this one I'm just going to add another one of the same, no reason. Doesn't matter which way you do it. 187, and then the last one is the bottom, and that's 16 by 11. And 16 times 11 is 176. So if I add 187 plus 187 plus 176, I get, oh, it's 550 again. So it's the same answer as the last one. That's just a coincidence. And again, it's square units. Okay, so now if I want to do the total area, I'm doing the lateral area plus the area of the two triangular bases. And I'm just going to draw it once and say times 2. So I see, if I think about it, I know this is 17 and I know this is 16. Now, if I actually want to, and I know both sides are 17, right? So it's isosceles triangle. So if I want to try to figure out the height, well, something nice happens because it's isosceles, I know that the altitude is, or the height is splitting the base of 16 into 2 equal parts. So I know just half of it would be 8. And if that's 8 and that's 17, I can solve to find the height using the Pythagorean theorem, or actually it's a special right triangle. So, or sorry, it's a Pythagorean triple. So I know if this is 8 and this is 17, then the other side must be 15. And that can allow me then to calculate the area of one of these triangles as 1/2 the base times the height. The base is the entire length of 16 again, because I want to find the whole triangle, times the height, which is the 15 we just found. So 1/2 16 times 15 gives me the area of one of those triangles, but I have 2 of them in my picture, so I do times 2. And now I'm adding to that the lateral area, which we got to be 550. So 550 plus 1/2 16 times 15 times 2, which ends up being 240. So I get a total area here of 790. Again, it's square units. Okay, so that concludes the example portion of the video. There is a U-try problem along the bottom in which you're finding the lateral and the total area. I do have a hint to help you out with the total area, which is that when you think about finding the area of the triangle and its equilateral, then what you can do is you can think, okay, I know the side is 6. I need to find the height, right? So I know this is 6 too. But I also know that all of the angles in a equilateral triangle are the same, so that means this angle over here is 60, which means the angle up here is half of 60 because it got split. So I see I have a 30, 60, 90 right triangle, and I can use that fact to solve for the height. So that's my hint. Give that problem a shot, and we'll be practicing more in class.